Welcome to this explainer. Okay, so today we're looking at a deeply ingrained cultural belief. You know the one. The idea that recycling mixed materials is always, absolutely, without question, the best thing we can do for the planet and our cities. It's a narrative we've literally all grown up with, right? But what if the hard data tells a totally different story? What if our current recycling infrastructure is actually failing us, mathematically, physically, and economically? We're going to explore some really fascinating source material today that outlines a massive paradigm shift. It proposes a total transition away from our traditional recycling habits toward what the author calls the post-recycling city. Okay, let's dive into this. Is recycling a thermodynamic mistake? I know it's a pretty provocative question, but we're going to look objectively at the facts, the physics, and the economics of what actually happens when we toss mixed plastics, paper, and glass into a single bin. Does trying to unmix all those materials actually defy the laws of physics? Does it drain way more municipal funds and energy than it could ever possibly save? Let's find out. To understand where we're at, we really have to understand how we got here. The source material points out that our current recycling model wasn't created because some brilliant engineers sat down and calculated the mathematically optimal way to handle urban waste. No way, not at all. It was actually born out of 1970s and 80s pollution fears. Early municipal incinerators had terrible emissions, and the public rightly pushed back. So recycling was introduced as this politically and culturally acceptable alternative. But, over the decades, that temporary fix kind of hardened into massive institutional inertia. We just kept building these single-stream sorting facilities based on old fears, totally ignoring the fact that technology and economics have radically evolved since then. So here's our roadmap for today. We're going to cover 1. The broken recycling paradigm. 2. The 4-stream model. 3. The thermodynamics of trash. 4. The economic reality. And 5. Building the post-recycling city. Let's get right into it. Section 1. The broken recycling paradigm. Why our bins are failing us. The core problem here really comes down to a fundamental concept in physics, entropy. Basically, entropy is the natural tendency of mixed things to just move toward disorder. When you throw a plastic bottle, a broken glass jar, and a cardboard box covered in pizza grease into a single recycling bin, you're creating a highly entropic, chaotic mixture. Think of it like trying to unbake a cake or, unmix a smoothie. To reverse that disorder, to perfectly separate those materials back into clean, usable, pure fractions, it requires a massive, irreversible drain of energy and labor. You can't just wish the contamination away, right? You have to spend huge amounts of energy to filter it all out. And that entropy, it creates this terrible domino effect of escalating costs. First off, contamination absolutely skyrockets the cost of sorting and washing. Second, material degradation kills your revenue. Think about it. Every single time a plastic polymer is melted down, its chemical chains actually shorten and degrade. It becomes lower quality. Paper fibers, they get shorter and weaker every time they're pulped. So you aren't really closing the loop, you're just delaying the landfill while producing a lower value product. Add in the wild volatility of global commodity markets, plus the massive capital needed for high-tech sorting machines, and you've got a system where costs structurally escalate instead of getting more efficient over time. Moving to Section 2, the 4-stream model, a new architecture for urban waste. Now, if single-stream recycling is failing us, what's the engineered alternative? Well, the source material proposes an entirely new architecture. It's called the Integrated Resource Recovery Center, powered by a 4-stream model. Instead of one giant, messy bin, households would separate waste into 4 very specific streams. First, burnables. That's plastics, paper, wood, and textiles. Second, organics, so food and yard waste. Third, metals. And fourth, glass and minerals. Now, the logic here is honestly brilliant. We keep metals separate because they actually can be recycled infinitely without degrading. We keep organics separate because they contain way too much moisture. But all those mixed plastics and papers, they're diverted into the burnables stream to be utilized for their massive stored chemical energy. When you break down typical urban waste, a staggering 65% of it is burnables. Organics are about 30%. Metals and glass make up just a tiny, tiny fraction. By recognizing that almost 2/3 of our waste is essentially fuel, just hydrocarbons and biomass, we completely reframe the entire problem. This perfectly sets the stage for our next major point about what we should actually be doing with all that stored energy sitting out there in our driveways. Section 3. The thermodynamics of trash. Physics over feelings. The thermodynamic reality here is just brilliantly clear. When you take a ton of mixed contaminated plastics and paper and run it through a modern waste-to-energy combustion plant, it reliably produces between 500 and 700 kilowatt hours of net exportable electricity. But if you try to mechanically recycle that exact same dirty mixed stream, the collection, sorting, washing, shredding, and remelting consumes between 2,500 and 4,000 kilowatt hours of external energy per ton. I really want to hammer home this 4,000 kilowatt hour upper limit. Let that sink in for a second. That is an astonishing amount of energy. The physics are crystal clear here. For heterogeneous, mixed, contaminated streams, mechanical recycling actually consumes vastly more energy than it saves. Trying to recycle low-grade plastics isn't saving the planet. It's actively draining power from the grid just to produce a degraded, low-value material. Mind-blowing, right? Section 4. The economic reality. Strict municipal budget optimization. So we know the physics don't support the current model. But ultimately, this comes down to the objective financial constraints of your municipal taxes. Every city has a strict objective function they have to balance, kind of like balancing a checkbook. To find the true cost of waste, you have to add up the cost of collection, plus transport, plus processing facility operations, plus landfill tipping fees. Then you subtract the revenue you make back. Now, in the legacy recycling model, revenue is practically zero because global commodity markets for degraded plastics have completely crashed. But in the integrated waste-to-energy model, you generate robust continuous revenue from selling electricity, selling recovered metals, and selling aggregate material for construction. So, what's the bottom line here? The data shows a staggering difference. A high-cost, heavily contaminated urban recycling program can cost taxpayers upward of $715 per ton to operate. Meanwhile, a fully integrated waste-to-energy resource recovery center, under really conservative estimates that fully account for capital construction costs, can drive the net municipal cost down to just $155 per ton. That is a massive, massive reduction in taxpayer burden. The source material gives us a very clear objective decision doctrine here. The magic number, the adoption threshold, is $180 per ton. If your city is currently spending more than $180 per ton to run a recycling dominant system, city leadership has a strict fiduciary responsibility to taxpayers to evaluate this integrated waste-to-energy alternative. It is economically irrational to continue spending more money for a thermodynamically inferior system. Section 5. Building the post-recycling city. From theory to concrete. Because let's face it, you can't just flip a switch overnight in a major metropolis. The transition has to be a staged reconfiguration. In years 0 to 1, you audit the baseline and pilot the 4-bin system. In years 2 to 4, you build anaerobic digesters to process the organics and start making biogas. By years 3 to 6, you commission the advanced waste-to-energy combustion lines. And by year 10, the whole system is fully optimized. Importantly, this model doesn't destroy municipal jobs. It just repurposes labor. Workers transition away from manually picking through dirty garbage on a sorting line and instead move into higher-skilled, much safer roles in plant operations, turbine maintenance, and emissions compliance. Now, any city proposing this is for sure going to face public pushback from folks remembering those dirty 1970s incinerators. The paper details strict mitigations to secure social license. Modern waste-to-energy plants are literal marvels of engineering. They use enclosed negative pressure intakes, so there is literally zero odor in the neighborhood. None. They use EU-class air pollution scrubbers, injecting lime and activated carbon to capture toxins, and most importantly, they feature public, real-time emissions dashboards monitored by third-party auditors. You're replacing vague reassurances with hard, verifiable data. I want to read this quote directly from the source analysis because it beautifully summarizes the entire thesis. Quote, "The integrated IRCR model reframes waste from a moralized recycling narrative into a thermodynamic and economic infrastructure problem. We have to stop treating waste as a symbol of our personal environmental guilt and start treating it as an engineering challenge that we can actually solve with the right infrastructure." Which leaves us with this final, absolutely vital question. Has your city's waste budget crossed the $180 per ton threshold? I highly encourage you to look into your own local municipal budget data. The physics and the economics are hiding right there in plain sight. Thank you so much for joining this explainer today. I really hope this sparked your curiosity to look a little closer at what actually happens after the garbage truck drives away. Keep learning, and I'll see you next time.